Okay, we'll go ahead and get started. One quick announcement. So in Canvas, I was able to figure out how to link the 2 chapter readings into Module 2. So you should see those as direct links. I think they're chapters 12 and 13 on mass spectrometry and infrared, and then the other chapters, nuclear magnetic resonance. So for this module, you'll have 2 separate exams because there's a lot of material that we're covering. The first exam will be on mass spec and IR, and then the second exam will have pretty much everything but focus more on NMR. And so I don't know exactly when that first exam for this module will be, but I think we have to go through 2 more lectures, so either next week or the week after. Any questions? So we had left off talking about isotopes. And isotopes are going to be important for us in understanding the way that mass spec data looks. And then we can use that to our advantage to determine the molecular formula from the data that it's giving out. And so just to recap that, an isotope is an element, so abbreviated E, that has the same atomic number, Z. Again, that's where it occurs in the periodic table. But the mass number A differs by the number of neutrons. So the number of neutrons is Z minus A. And so that's the nomenclature. So again, for carbon, the sort of stable isotope of carbon is abbreviated like that. That's what we're all made of. And then we have a little bit of this next one, carbon-13. The radioactive one is carbon-14, and that's lesser abundant. It's made synthetically. There's also another one, carbon-11. The radioactive ones, so 11 and 14, we're not really going to talk about. So 12 and 13 are the ones that are pertinent to this discussion. And so the ratio of those isotopes, and I'll explain it conceptually, mathematically on the next slide, as well as what is important to us. And then some of the ratios, the heteroatoms, are also important. And that translates visibly how you interpret the mass spec data. So here are the elements that we're interested in. And I want to just run through carbon real quick so we understand what these numbers in the abundance column mean. So carbon-12 is defined as having a mass of 12 dot and then 0 repeating. So that's sort of the standard we're going against. The stable isotope 13, you see that we've added that neutron, so the mass increases, and it has some stuff after the decimal. But if you look at the numbers 98.93 and then 1.07, you'll see that equals 100. So conceptually, what does that mean? If we consider 100 molecules of methane, CH4, so you have this container, within it there's 100 molecules of methane. Essentially, 99 of those molecules will be C12H4, and one of them will be the C13H4. So within this nomenclature, just that CH4, it has no superscript. If there's an appreciable abundance of another isotope, you just have to recognize that it's in there. But for the most part, we're not explicitly stating like carbon-12. But within there, that 1% of all of those molecules is going to have a carbon-13 nucleus. So as we look, nitrogen-14, that's pretty much 100%. Oxygen, you see three of those labels there. That's also about 100%. The other ones don't, rise above the threshold of 1%. Fluorine, F19 is 100%. Now the next one, chlorine and bromine, are interesting. So notice that they both have two isotopes, stable isotopes. So chlorine has 35 and 37. And so again, that's the mass of that element. And then look at these ratios, 75-25. So essentially that's 3-to-1. Bromine has 79 and 81. And they're in a ratio of 1-to-1. So to put that into like conceptual terms, say you had now, instead of methane, you had chloromethane. So for every 100 molecules of chloromethane, so 75 of them would have that 35 Cl. And 25 of them would have the 37 Cl isotope. So that's how these elements exist in nature. Where this can get complicated, because as we saw before with methane, I'm not a mathematician or anything, but this gets into statistics and probability. So you can now imagine that, that carbon can still have a 12 or a 13 label. So you can use those abundances to say that, there's going to exist a molecule that could have a 13 labeled carbon and a 35 labeled Cl, or any like permutation thereof. But as you start, putting these labels in there based on the percentages, that number of molecules becomes smaller and smaller based on the statistics, how that falls out. It's going to become visually apparent to us as we, again, look at the mass spec and we consider the parent ion. So iodine is 100%. It's not terribly useful to us in terms of a diagnostic. The question was, given this number 288, can we figure out the molecular formula of C19H28O2? So we don't have imagine you don't have the structure in front of you, you just have that data. We want to first figure out a molecular formula, then we can look at degrees of unsaturation, and then maybe start making some structural claims. The reason that we can do this, that we can answer this question, lies in those isotope abundances of those elements. So because for any element there are those isotopes, the natural abundance numbers we can use to our advantage. And to frame this question, we want to figure out the C19H28O2. Oxygen is really difficult to determine. Because it's so difficult, we're going to look at excluding other elements first, and then through logic, we'll end up back at oxygen to support our claim that it is in there. So to exclude the presence of the other heteroatoms, nitrogen, fluorine, chlorine, bromine, or iodine, we're going to use their isotope abundances. We're going to visually look at the mass spec and say, okay, is it there or not there? Just purely based on those numbers from the prior chart. And then once we understand that, there's a very simple equation we can use that's going to tell us exactly how many carbons a molecule will have. And then from that, we got a little piece of data. Knowing what we know about Lewis dot structures and bonding patterns, we can then start from that number of carbons n, determining hydrogens, and whatever's left over, we can start assigning to heteroatoms. And the reason we can do that is these heteroatoms will have signatures in the mass spec. So it's partly understanding the concept, but really, when you look at the data, it's visually recognizing, is something there or is it not there? And as I said, oxygen is the toughest element. So we're going to infer its presence by excluding or including these other ones. And so the thread to infrared spectroscopy is that we learned a lot of functional groups that do contain oxygen, and the infrared data is going to give you explicit signatures of those different oxygen-containing functional groups. So you have alcohols, which are OH, carbonyls, which are carbon-oxygen double bonds, and then they all look different. So if you're able to sort of recognize the pattern, like we all know what a stop sign is defined to be. So you have this red octagon, you know to stop. It's the same sort of learning principle. The shape of the signal looks this way. That means it's going to be this functional group. And the point of this exercise is you really have to pull different pieces of data from these different techniques to make a claim with evidence to support, okay, it has this many carbons, this many sets of hydrogens, this other heteroatom containing functional group. And as you do that, you're building up confidence to your argument. So what are the signatures that we want to pay specific attention to in terms of these other heteroatoms? If the molecule contains nitrogen, the mass of the parent, so this nomenclature we're using for parent is that square bracket M. So parent means all the elements in the molecular formula. If the parent mass number is odd, that means there are an odd number of nitrogen atoms. So that's one diagnostic. If the parent number is even, it can have an even number of nitrogens. And that's going to be a little bit more ambiguous, which will require the use of IR spectroscopy to help verify. Fluorine, since it's 100% abundant, and when you incorporate it into an organic molecule, it's going to give you an even mass. So you don't really have a nice diagnostic signature. chlorine, since there's two isotopes in that 3-to-1 ratio, the parent region is going to show you that visually by the percent abundance of the parent. So this is your parent M, and then in this nomenclature M+2. The difference between 37 and 35 is 2 mass units. So you're saying the parent plus 2 mass units. And that will answer the question of, okay, you have this molecular formula at a certain mass. Why do you have lines greater than that mass? It's due to these other isotopes being present. So we can say parent plus 2 mass units. The same logic will hold true for bromine, except now the ratio of the parent to the parent plus 2 is 1-to-1. Although iodine only has the one isotope, 127, it still can give you a signature in that once the parent degrades or fragments, you might see a peak at a mass of 127. That would correspond to iodine ion. Or if you take a fragment ion and subtract 127, that difference is implying that iodine was in the molecular formula. So conceptually, those are the rules of the game. And now what I want to show you is visually, what are you looking for when you interpret this data? So I pre-wrote some notes here so I didn't forget. Nomenclature, your parent, then your parent plus 1. The M to Z, that's your x-axis. What are those numbers? And then the abundance. So for all of these slides or compounds we see coming up, they're all going to be of this form. There's this benzene ring, and then there's a substituent. And so we're really looking at how did that heteroatom X substituent, what unique signature does it give in mass spec? So the first compound we're looking at is called aniline or aminobenzene. You can see that the molecular formula here is C6H7N. If you did the normal operation, 6 times 12 plus 7 times 1 plus 14, you would get a mass of 93. So the molecular weight of aniline is 93. That's an odd number, right? So it's hard to see, but that number right there is 93. And so what we then infer is that the compound has an odd number of nitrogen atoms. And as I said, the parent that has all the elements in their ratios of the molecular formula, that mass. But now look beyond that. See right beyond that, you have these extra 2 numbers. So 93, and then you have 94. So 94 would be the parent plus 1, M plus 1. So that's listed here in this chart, 93, 94. And then the third column is you're going to the top of that signal all the way over here in looking at the abundance. So for that parent peak, that's at 100% abundance. You do the same thing for the M plus 1. You draw a line over, and you're sitting at somewhere around 6.5. So you can count in this molecule, there are 6 carbon atoms, right? And through some logic, you can rationalize why this number is about 6. Because from the natural isotopes, or the natural isotope abundance of carbon, remember we said it was about 99 to 1 for C12 to C13? So you're getting that extra 1 because of that C13 atom. The mass spectrometer is able to detect when you have that carbon 13 somewhere in one of those molecules. The practical aspect of this is not only for determining the mass of an unknown substance. Any student athletes in the crowd? If not, you're probably familiar with like professional sports in the Olympics. And there's rules on banning substances, right? Like you can't take artificial performance enhancing drugs. This is the technique that is used to determine if an athlete has been doping. So typically the athlete provides a urine sample. The urine sample is then analyzed. And what they're scanning for is the presence of substances that your body does not naturally produce. So everyone in this room, your body produces testosterone, which is a hormone that induces these biological processes. It produces like a specific percentage of that. If someone's doping, they're going to have more of that. And then the signature in the mass spec is also going to look different than biologically produced testosterone. And so then they can infer that because this pattern does not look normal, this person has extra testosterone in their system. So whatever the spectrum of performance-enhancing drugs is, they scan to look for these things. So odd number means odd number of nitrogens. That's the signature there. For fluorobenzene, we're trying to determine the presence of fluorine. This has the molecular formula C6H5F. Notice the mass is even, 96. There's really nothing unique about a mass spec when it contains fluorine. So it's hard to infer that it's there. But there are other instrumental techniques that will allow us to determine if it is. So fluorine's a little bit ambiguous at this point. For chlorobenzene, C6H5Cl, notice now the parent is at 112. So this is your M plus. So 112. Then if you look at the next tallest peak after that, it's 114. So that's M plus 2. The superscript plus means these are ions. That's what the instrument detects. So you have an M and an M plus 2. If you draw the lines over to the y-axis, you get these numbers, 100%, 32%. So that's basically your 3-to-1 ratio. It's saying that that mass is coming from the compound with the 35 label. And then this mass is coming from the compound with the 37 label. So when you look in that parent region and you see an M with an M plus 2 of that 3-to-1 ratio, that's telling you there's a chlorine somewhere in that molecule. So visually, I mean, even without sort of drawing the line to the y-axis, you can see it's about 3 to 1. So now look at the bromobenzene. And if you focus your eyeball at the parent region, these two numbers, so we have 156 and 158. Notice the heights of those peaks, they're about the same. And the actual numbers here, 197. That's the 1-to-1 ratio. The 155.95, that's due to the bromine with the 79 label. And the 157.95, that's bromine with the 81 label. And to repeat, the reason you see them is because bromine naturally has two abundant isotopes. And the difference is due to the number of neutrons. Iodine, we said, it's a little bit more diagnostic than fluorine, but not much. So C5 or C6H5I, you get a mass that's essentially 204, even though it says 203.9. It might look odd, but it's still an even mass. So here's your parent. And then the signal at 127, that's due to an iodide cation. That's what you're seeing, is just the I atom. And to point out here, so let me write this. So C6H5I, that parent is corresponding to that intact molecular formula. See this other fragment here? It's at a mass of 77. So the reason you're seeing that signal is because that intact molecular formula is losing iodine. So it's no longer there, and then that's a mass of 127. So if you do the math, your 204 minus the 127, you get that signal now at 77. And so it would correspond to those elements for that fragmented signal. So that one's a little bit more subtle to see what the signature is. Any questions before we do some of these leap exercises? So based on all of that, now I really want to be explicit about the nomenclature here. Again, M is your parent, M plus 2 is your parent plus 2 mass units. And the way the question is phrased is the numbers in the columns are telling you the abundance of those ions. It's not telling you the mass, it's just telling you the ratio of the parent to the parent plus 2. So based on those abundances, which answer do you think would have a bromine in the molecular formula? So it's going to be C. So the parent at 100 and the parent plus 2 at 97. That's a 1-to-1 ratio. And so as you're accumulating this data, you could say, what can possibly be structurally in there? The way I represent it is like a squiggly line that's bonded to something and then a bromine. So we know that there has to be a bromine in there. Then we can use other features to make some fragments, and then eventually we'll piece it all together like a jigsaw puzzle. So based on the ratios, which of these responses would then have a chlorine? So this would be A, and again, that would be your chlorine 35, and this would be your chlorine 37 contribution. So these can get a little tricky in the sense that you have to pay attention to the nomenclature: M, M+1, M+2. So chlorine and bromine are specifically looking at your M+2 contribution. So now, the data you're looking at for this problem, or you're looking at actual masses, the M to Z, so the x-axis value. So given these weights, which one would contain a nitrogen atom? So it would be B, because that's an odd mass. So that's the diagnostic signature you're looking for. So just from understanding that, right now what you can say is, okay, I have a nitrogen. I know nitrogen has a lone pair. It's going to have these three things bonded to it. And as we learn IR and NMR, then we can start saying, okay, what are the things bonded to it? So still in the context of, this testosterone problem, we're trying to figure out what the molecular formula is. How can we start applying some of this, based on the questions we're given? If we have a compound with a parent ion mass of 46.04186, the reason you see so many decimal points is because of how those different isotope abundances contribute to a mass in a molecular formula. The more decimal points you have, the more it narrows down the possible combinations of elements that you can stuff into that number. So it says explicitly that mass contains one oxygen atom. So given that, what's the maximum number of carbon atoms that can then be present? So let's walk through it to see how we get to that response. We're assuming there's C and H, so that's agreed upon because this is organic. And it's telling us there's one oxygen. So we're going to subtract out the contribution from oxygen. And that mass is 16. So that gets us 30. And all of that 30 has to contain the C's and the H's. And so now, because carbon is the bigger mass, what we're going to do is take that 30 and divide by 12. And so you're going to get a maximum of 2, right? Because 2 times 12 is 24. It can't be 3, because now you're at 36, and that's beyond what you're allowed to have. So 30 divided by 12 gets you 2 carbons. So we have C, 2, H, I'm going to say X, and then O. then we can say 46 minus 16 minus 24. That gets us how many remaining? 6. So our answer for this is 2 carbon atoms, but through that logic, we're then able to determine that the stuff remaining has to be hydrogen. So overall, C2H6O. So let me just sort of put this all in perspective. Now that you've done that, how many degrees of unsaturation does that molecular formula have? 0. So no degrees of unsaturation. Now, if you had to expand that C2H6O into possible structures, because you have an oxygen, what functional groups can you have in those constitutional isomers? What was the first one? Ethers and alcohols. You can only have ethers and alcohols. You cannot have anything with a double bond because there's no degrees of unsaturation. So if you say, okay, now I need to draw stuff with 2 carbon atoms, that's an ether. How would you do that? So that would be an ether. That would be an alcohol. And so those are our 2 claims. And then the next question would be, given if we had some substance, how do we know which is which now? And again, that's where the infrared data is going to come in handy. Because the difference in IR between an ether and alcohol, they have unique signatures you're looking for. Any questions? So we're 100% confident that we always have C and H. We're not sure about the other heteroatoms, but nitrogen, chlorine, bromine, and iodine have signatures that will indicate if they're present. That really leaves us with oxygen and fluorine. For the purposes of this discussion, we're going to focus the most on oxygen. Fluorine would use a different technique. When we come to NMR, we can talk about that. But right now, we're focusing this on how do we know there's oxygen there. So over the next couple slides, we're going to look at how we can use the M in the M+1 abundances specifically to determine the exact number of carbons. From that, addition, subtraction, and the math argument, we're going to get some remaining number that includes our H and then oxygen. And from that, we then determine some ratios that make sense. So again, here it is. There's the testosterone mass spec we introduced last time. There's the molecular formula. There's the mass. We're trying to determine the molecular formula from that 288 number. And now we're going to use these ratios here. That's the M and the M+1. See how the molecular formula has C19? Now look at the M+1 number. The abundance says 20.5. So it's not by coincidence that those are pretty similar, almost the same. And again, the M+1, M+2, those are beyond what you see in the parent mass. Let me backtrack here. So we look at that number 288. Because that number is even, we're saying the molecular formula cannot have nitrogen, or an odd number of nitrogen. If we look at the M in the very tiny M+2 ratio, so 100 to this 2%, that will also reject chlorine and bromine from being present. There's nothing really in here that would indicate iodine in terms of a 127 peak. So we're rejecting all of those as possible elements in the molecular formula. So when we looked at that, and so now the equation that we can use to our advantage is shown here at the bottom. The exact number of carbon atoms is equal to this quotient here, where you have abundance numbers. So these are not mass numbers. So if you look at the M+1 abundance and you divide that by the abundance of M, and then overall you divide that by 1.1, that's going to give you the exact number of carbons. And this equation, as I said, falls out from that 99:1 of C12 to C13. So when we initially introduced this on Monday, we were doing it from more of a first principles aspect, where you just had like the number 288 and we divided by 12. That was giving you the upper bracket of the total carbons that could be there. This equation is giving you the exact number. So these were the abundances. So your M was 100%. Your M+1. So again, what I just wrote there, the M+1 is due to the carbon-13 contribution. You have 100% and then 20.5%. So when you do all that, we already know that the answer is going to come out to 19. Because we went through the exercise where we saw testosterone and we just counted the carbons visually. You shove it into this equation, it's going to spit out 19. So 19 carbon atoms. So if we take 19 carbons times the mass of carbon, so 19 times 12, that would get us 228. So 228 mass units belong to carbon. So we're slowly building up from that number, the number of carbons. Now we have to figure out, okay, how many hydrogens, and then whatever's remaining, we're going to assume is due to oxygen. So we put all that stuff in the, this should say exact, this equation, exact number of carbons. So again, use abundance numbers. That gets us 19. We multiplied by 12, and we saw that carbon's contribution to the 288 is 228. Questions about the logic so far?
These questions, ones we see like on our test, like, is this something?
Yeah, they'll basically, they'll be the same logic. The molecules probably won't be as complex, so it'll be, there'll be smaller carbon counts, but you'll be expected to like shove numbers into these equations and figure out what's the carbon count, what's the hydrogen count, or if you're given a piece of like mass spec data, look at it, which heteroatom is present, and then you're slowly building up to a molecular formula. So typically the way I design these is, for like a series of 5 or 10 questions, you're building up to figure out what it is, what functional groups could be there, what can't be there. So it's just different ways of attacking the problem. So pay attention to the wording of this. We have N equals 19. We want to figure out for 19 carbons, what would be the maximum amount of hydrogens you could have. And we would use this alkane formula. And then we take 2 times 19, we add 2. So for 19 carbon atoms, the maximum number of hydrogens you could have is 40. So if we had, the 228 contribution, now we have 40 as the maximum. We're still not up to 288. So what that's telling us is there's something else in there, some heteroatom. So our parent was the 288. So if we add that together, we get, 268. And then we can say 288 minus the 268, that gets us 20 mass units that are unaccounted for. So through that, there's something else there, and then the ratio between the hydrogen and whatever else is there, we still have to figure out based on some simple ratios that essentially is going to equal 60. So the 40 plus the 20, that's going to contain the hydrogen plus the heteroatom. And then from that, we have to figure out what ratio are they present in. And this summarizes our findings so far. We got the carbon count from the equation. We got the max hydrogen count, sort of using, well, I'll just say from alkane formula. And then the issue is we're still left over with this 20 mass units to deal with. And as the bottom of the slide says, we have to figure out the exact ratio between hydrogen and oxygen that's going to equal 60. And then from there, we have the confidence to make a claim for that molecular formula. So it's like CX, or sorry, HX plus OY must equal 60, where we're figuring out what are those X's and Y's. Since oxygen has a greater mass than hydrogen, the way this table is arranged, oxygen 16, hydrogen's 1. Under the oxygen column, we're just increasing from 1 to 2 to 3 to 4. And then if we take, 1 times 16 is 16, then we subtract it from 60. That's the number that you're seeing in the hydrogen column. So which one of these do you think makes the most sense? 2 and 28. So that's going to be the right answer. I mean, we already know what the molecular formula is, but this just shows you how we bracket it. The distractor responses here, see this number 44? It can't be that, right? So that's greater than 40, which was the max number of hydrogens. It can't be D, that number is negative. You can't have like anti-hydrogens. So that doesn't make sense. So really we've bracketed it, and now we have these two plausible cases. You could say, well, why can't it be 3? And then just through chemical intuition, that's a valid molecular formula, C19H12O3. But when I look at that, I'm like, I have 19 carbons, but only 12 hydrogens. Like, that molecular formula is going to have a lot of degrees of unsaturation. So it's getting into realm of, yes, it's possible, but it's probably not the best fit for what we're looking at. So a lot of degrees of unsaturation, a lot of pi bonds, a lot of rings. And so it's not the best fit for this. And then using that same argument with our oxygen count, because we were limiting that due to 16, that gets us the mass contribution of oxygen. So that's, again, that's what that column means. If we take 60 minus that mass contribution, that gets us our hydrogen count. And then we see in green that that's the best fit. So again, in constructing your claim from the data, as you make your argument, you want to put these brackets on. And then as you get possible claims that you can make, that's when you need to use a little bit of intuition. So, I mean, that's what we came up with through this exercise, C19H28O2. as we looked at this number 288, we were able to use our reasoning to come up with the molecular formula that does match the structure when you're given it. You're just counting the C's, the H's, and the heteroatoms. So now you're able to do it from the opposite perspective of just the parent mass. Any questions before we move on? And since we have some time before we get to the rest of the stuff, what I can point out is the title of the slide says, it says molecular fingerprinting. So we all know that in law enforcement, one thing they'll do at a crime scene is they'll dust for fingerprints. And the reason they do that is because everyone's fingerprints are unique to them. You kind of have that little, peak in the middle, and it like spirals out in different patterns. So that's unique to you. And so the mass spec for each compound is unique to each compound. Not only do you have the parent mass, but all of these different fragment patterns are unique to those compounds. And so as I said, another example is like with narcotics and narcotic trafficking. Fentanyl is invoked nowadays quite a bit, as fentanyl smuggling into the US. So mass spec can tell you, is fentanyl there? It can even go so far as to tell you where that fentanyl is being produced. Is it being produced in this country or that country? And the reason people are able to do that is because then you can see how that fentanyl is being made. What chemicals is it coming from? Those chemicals will all have their own unique molecular fingerprints, so you can, as a detective, trace back to the origin of where something is coming from. Any questions? So the last part before we finish up for today is setting the stage to introduce infrared spectroscopy. And as I alluded to a little bit earlier with that CH255, the fact that you can draw two claims and they have different functional groups, IR is going to be useful to helping us say, okay, it has to be an alcohol and it cannot be an ether, or vice versa. And so we'll apply all of this logic to these questions going forward and see we arise at the same situation. So then what else do we need to introduce to help figure out what an unknown substance is? So there's the statement or the question. I've just rewritten the data from that in a tabular form to help us see any patterns here. And getting back to that sort of what's going to be on the exam, these are the skills, the learning outcomes that you should be able to demonstrate your understanding of this. So when you look at this data, there's your parent, and notice now it's saying parent plus 1. The parent has a mass of 72, parent plus 1 is 73. At 72, that's 100% abundant. Parent plus 1 at 73, that's 4.3. So a couple things to write, just make note of at this point before we move on to the next couple slides. So the parent mass is even. So that means there's no nitrogens or an odd number of nitrogens. The data that's presented to you is M plus 1. It's not M plus 2. So there's no chlorine or no bromine. And then you can estimate the total number of carbons from that M plus 1 percentage. It's 4.3. And so you're dealing with about 4 carbon atoms. That's what it's telling you. So your parent is due to the carbon-12 contribution. The parent plus 1 is your C13 contribution. And that's giving you sort of a starting point of the total number of carbons in the molecule. So we see that that number is about equal to 4. So given M with a mass to charge of 72 at 100% abundance, M plus 1 mass to charge of 73 at 4.3%, which of the following heteroatoms is most likely present? So it's got to be B, oxygen. So nitrogen out because the mass is not odd. Chlorine, bromine are out. Because there's no M plus 2 data. So we can conclude that the 72 has carbon, hydrogen, and oxygen. Now we can shove those percentage numbers in there. So you get like 3.9. But again, we have to deal with integers for this. So we're going to say that's 4. And again, that's, something as you do these problems and you develop your intuition, you're going to have to, make that decision. So we're going to say there's 4 carbon atoms. So the parent was 72. We found there's 4 carbons. 4 times 12 is 48 mass units. So due to carbon. So that gets us how much remaining? So 58, 68, 72, that's at 24. So we have 24 mass units, and now here's a table with some ratios. Is choice A reasonable? So no, because, for 4 carbon atoms, 4 times 2 is 8 plus 2, that's 10. The maximum number of hydrogens is 10. So that's got to be wrong. D has to be wrong, because we have to have some hydrogens. Now the choice is between B and C. They both have 1 oxygen. So they're both contributing 16. But then the hydrogen count is just basically getting you to the remainder. So it would have to be 8 hydrogens. So that would get us to C, because the math from choice B does not add up. So we would end up with C4H8O. So the maximum number of hydrogens would be 10. We have C4H8O. We remember that oxygen will not change the hydrogen count. So we're left with H2. A degree of unsaturation was H2, so that's going to get us 1 degree of unsaturation. And so we can think, that degree of unsaturation, can be a pi bond or a ring. And so now there's a lot of possibilities for constitutional isomers within that molecular formula. So our last slide here before we wrap up, there's 1 degree of unsaturation. Which of the following is not a viable combination of possible functional groups? Ester. Why not?
Because it has 2 oxygens.
So the ester functional group must have 2 oxygens. That's how it's defined. We determined there was only 1. And so what now is, what's A, B, and D telling you? they're all possible functional groups you can have within that molecular formula. So if we had 4 carbon atoms and we wanted to make a ketone, that could be a possible structure. So the degree of unsaturation is the pi bond. In choice B, the degree of unsaturation is a ring. So if we had 4 carbon atoms in a ring, and then we plopped in an alcohol to take care of the oxygen, that could be a constitutional isomer. And then for choice D, the degree of unsaturation is now a carbonyl, but it's at the terminal carbon of the chain. So those would be 3 possibilities of isomers for that molecular formula. And so now in one sense, we've taken the number, we've generated a molecular formula, but now we're in a pile of shit here because now we have all these possible structures we can choose from. So of that set of isomers, how do we then narrow it down to something more specific? And so that's where IR will come in, because all of these functional groups, the ketone, the alcohol, the aldehyde, will all have unique signatures by IR. And so as we look at that data, we're going to take a very qualitative approach to interpreting that data where it's very visual. We're not going to do a lot of math. We're not calculating things. You're saying, okay, in this one region, I see this shape. That shape looks like an alcohol. Or in this other region, I should see a carbon-oxygen double bond. Is it there, yes or no? It does get a little subtle in the sense of in your ketone, you have that carbonyl, right? CO double bond. But you also have a carbonyl here and an aldehyde. If you have 2 functional groups that are kind of show the same signature, how then do you make any further decisions? Well, it turns out the location of that carbonyl on the chain makes a difference. An aldehyde carbonyl looks a lot different than a ketone carbonyl. So we're working through this flow chart of how things look to zero in on things. So that's where we'll end today. Then next week we'll start with IR. So within the module where you find these lecture decks, I would encourage you, there are some other links to watch. One of them is like a screencast I talked through. The other one's just a PowerPoint of the different functional groups for the IR. So you want to make sure you look at that before coming into lecture on Monday so you have an idea of what we're talking about.